All right, so for chemical equilibrium, we're looking at a special type of reaction. All right. So to get the process starting, if you have a container, all right, with water, and you just leave the container with the water, what will happen to the volume of water over a period?
Yes, sir. Well, now I hear you, sir.
All right, let me exit and come back. I'm not sure what is happening.
Yeah, yeah, no. Yeah, yeah, no.
Other persons are hearing me.
Yeah, now yeah, no.
All right. Right, so I was saying, if you have an open container with water present, what will happen to the level of the water inside of it after a few days?
It will reduce.
It
Decrease.
Right, it will decrease. However, if you have a bottle of water and it is closed, what will you observe? So if this container is no longer open, so then let me draw next one. If it's a closed container with water inside of it, what will you observe after a few days?
Bubbles are formed on the top part.
At the top right, so you will see droplets of water on this side, right? Can anybody tell you what is happening while we have the droplets of water on this side?
The evaporation are taking place.
evaporation, sir? Yeah.
All right, so the water would have evaporated, right? However, it's a closed system. That means when the water is escaping as a gas, what happens afterwards?
It condenses again and form back water.
That is correct. So because the system is, because the container is closed, the product, so what you have is water, you have water as a liquid, right? It is being converted to a gas. In this container, this is what happens. Water, liquid is converted to water in the gaseous state. So it escapes, all right? And that is the reaction, it's completed in that way. However, if the container is closed, what we have occurring is that the product here, it cannot escape, right? And we have a second reaction occurring where the gas is being converted back to a liquid. So the reason why you see droplets on the sides is because we have two reactions taking place. The forward reaction is what? What process?
Evaporation.
Evaporation, correct. And the reverse process is?
Condensation, sir?
Condensation. So you realize if the container is left open, we only have one reaction occurring, right? When it is open, going from the liquid to the gas, and it is allowed to escape. However, if the container is closed, the product of the forward reaction is not allowed to escape, and that now gives the opportunity for a reverse reaction to occur. So, did someone want to ask a question?
No,
All right.
sir.
All right. So the first thing, how was it possible for us to get a forward reaction and a reverse reaction?
When the
Sir,
system
because
was closed.
yeah.
So the system is, right? So when the system is closed, that is what gives us the possibility of having a forward reaction and a reverse reaction. Because when it is closed, the product of the forward reaction is not allowed to escape. And so the reverse reaction is possible. Now, the next question is, will the level of water stay the same? So even though none is escaping, right? In the closed container, will the volume of water stay the same as it was before?
Yes, sir.
Yes,
You
sir.
sure? You sure? So the
Sir,
correct.
half of it.
So if you have water droplets on this side, where did these water droplets come from?
Water.
Condensation.
Right, but they would have been formed when the water molecules escaped as a vapor and then condense. So if you have water molecule on this side, then will the volume of water here be the same?
No, that decrease, okay?
It will, that is correct. So let me just erase the water molecule of this side, right? So let us say we have 50 cm cube of water. And then now some of it will evaporate, right? But because it's a closed container, all right, so before I do that, when it evaporates, let us say the volume, it drops, all right? So that was the original volume, right? And I'm going to use a broken line to where it decreases. So this was the original volume, evaporation occurred. So some of the water molecules would have escaped, and as a result, the volume would have decreased. All right, so that is what happened. However, the system, the container is closed, so the gaseous water molecules cannot escape the container, and we have the reverse reaction. And so we have condensation taking place, right? That means some of the water molecules will re-enter the liquid phase. Now, what will happen to the level of water here when condensation occurs? What will happen to the level of water again?
It will increase again.
All right, it will increase again. So here was the original OR or original. When evaporation occurred, it dropped to here. But remember, it's a reverse reaction. And so some of it will come back as a liquid. But meanwhile, the gaseous molecules are converted to a liquid. More of the liquid is going to be converted to a gas. So what is going to happen? The level of water, it will increase again, but it will not go back to the original. So it will increase again, but it will not go back to where it started. And the reason for that, we have a reverse reaction occurring. So as more products are converted, so as more water vapor is converted to the liquid, we also have liquid being converted to the gas. Is that clear? Do we understand this?
Yeah, man, sir, we get it.
Yes, sir.
So what you should remember, and the reason, right, And what will happen now is that it will reach a point where the volume is not going to change. So let us say at this point where I have the broken line, the rate at which the liquid is being converted to the vapor is also equal to the rate at which the vapor is being converted to the liquid. That means both of the rates are now equal. Will the volume change again once the two rates become equal?
No, sir.
No, exactly, good. So what I want to point out, when you get to, when something is at, let's say at equilibrium, right? And you interfere with it. So when we get to Le Chatelier's principle, I'm just showing you from now, if you have something at equilibrium, right? So let us say the original one was equilibrium. When you interfere with it, you will never reach it. When you get to equilibrium again, it will not be at the original point. So the original volume was here, right? Evaporation occurred and it decreased to here. But because it's a forward and reverse reaction, the volume it increased again, but not to where it was initially. Right? So in an equilibrium reaction, if you have something at equilibrium and you interfere with the equilibrium, right? And I'm starting to use the word equilibrium without explaining it. All right, so at this point, can someone tell me what happens here? So we have the two rates occurring, right? What term do we use when we have a forward reaction and a reverse reaction taking place and both of the rates are equal?
Dynamic.
Dynamic equilibrium.
Dynamic.
All right. No, you just said dynamic, right? Why, what does the term dynamic mean?
When the both forward and reverse reaction take place at the same time.
Something is because chemical equilibrium is when both the forward and reverse rates are equal. But if it is
Sir.
dynamic, something else.
So the products are continually being converted to reactants and the reactants continually being converted to products.
Right. But and you won't notice anything. So let us say an equilibrium reaction is occurring, right? And how you know you reach equilibrium is when you get a color change. So let us say you're looking for a blue color. So when you see the blue color, you know that equilibrium is achieved. So when you see that blue color, let us say it was changing from, let's say green to purple or something, right? And when you get blue, it's at equilibrium. So at equilibrium, it is not going to change from blue again. So it will appear that the reaction has stopped. However, it has not stopped. It is at equilibrium. But because you won't see any more physical changes, right? It will appear that the reaction has stopped. However, reactants are still being converted to products, and products are still being converted to reactants. So equilibrium, both the forward rate and the reverse rate are equal. But when we mention the part about dynamic now, is because the reaction, it does not ceases. Reactants are still being converted to product, and products are still being converted to reactants. But because the two rates are equal, you won't see any changes that you can, there won't be any change that you can see or measure. It will appear constant. Macroscopic, that is correct. Right. So you won't be able to see any change, and that is why it would appear to have stopped, but it hasn't. So you can just, so when we say dynamic, you're correct in that both rates are equal. but you must also add that the reaction is still ongoing. So that part is key as well. Even though both rates are equal, you won't observe any changes, but the reaction is still ongoing. So reactants are being converted to products and products converted to reactants. All right. So that said now, what are some, if you have a system now at equilibrium, what are some of the features?
Equilibrium can only be achieved in a closed system.
Sorry, just a second. Yeah, go ahead now.
As one feature, the equilibrium can only be achieved in a closed system.
All right, hold on. Just a second. A call was coming in and the volume it jumped as a result. So I'm not hearing you, so I'm just going to exit and come back. All right, so just a second. I'm just exiting and come back. Right, you can go ahead now. The person that was talking earlier.
Yeah, I was saying equilibrium can only be achieved in a closed system. It's the first feature, right?
Right. It must be a closed system. Correct. Anything else?
Equilibrium can be achieved from any direction.
What do you mean by any direction?
Any direction.
Oh, so all right. So we should say that what the forward rate and reverse rate are equal. Anybody else? And we said that it must take place in a closed system.
You want the next one, sir?
Yes.
Macroscopic properties are constant. Microscopic properties are continuous.
As we mentioned that the macroscopic properties are constant, when it comes to concentration, the concentration of your products and the reactants at equilibrium, they are not equal, they are constant. So don't put that the concentration at equilibrium is constant. Sorry, are equal, they are constant. So, let me just put it on the side now. So concentration of reactants and products are constant. Should the temperature be constant?
Yes, sir.
All right. So we also have to ensure that the temperature is constant.
Why is that? Explain it.
So when you're going to calculate the values, so we have the equilibrium constant and temperature is the only one that can change the value of your equilibrium constant. Sorry, this person is calling again. Just all right, right. So I was saying that for this one, if you change the temperature, the value you would obtain for Kc, it will change it as well. So we have to ensure that we do it at a constant temperature. And this part also tends to come in questions where they ask you about the effect of changing the temperature and the value of Kc. So when we're looking at Le Chatelier's principle and how it, and in terms of temperature, we're going to see how it affects it. All right. So we're going to go right into that aspect. Pressure, concentration, catalyst, right, just the temperature. Right, so we look at equilibrium, dynamic equilibrium, and the conditions at equilibrium. So I'm going to look at Le Chatelier's principle and do some calculations. Can someone just speak? Let me see if the audio is clear on your end, because a call came in, so it probably dropped. No, all right. I'm going to have to exit it again because I'm not. Whenever a call comes in, the audio on the phone it drops.
Daniel, 4 months.
Give me a second.
Take off, mister. Take off my flipping. Me never tell her, take them off. Take off, mister.
All right. So before we do the calculation, let's just get Le Chatelier's principle out of the way. All right. So does anybody know what Le Chatelier's principle says?
When the reaction is disturbed, the equilibrium will shift to the left or right to maintain Kc.
Does anyone know it? Right. So once you have your system at equilibrium, if you apply any form of stress, the system will shift in a direction to counteract it. Right? So if a stress, and you can put this in your own words, right? Just remember that the system at equilibrium, if you apply a stress to it, it will shift in a direction to counteract it. Okay. So if a system
Sir, somebody asked you for the physics and bio now.
bio, not physics. So if a stress is applied to a system at equilibrium, the equilibrium will shift in a direction to counteract the stress. All right, this part of equilibrium, it's supposed to be kind of easy, but students tend to mix it up a little. All right, so I'm going to start with concentration. So we're going to do concentration, pressure, and temperature. By the way, does catalyst affect the position of equilibrium?
No.
No, sir.
What, what does it do?
Speed up the
It
That
just
is
process.
Speed up the
easy.
rate of the forward
Reaction.
and the backward reaction.
Right. So it just allows equilibrium to be achieved quicker. All right, so the first stress. So when we say we are applying a stress, we are either going to be changing the temperature.
Sorry, I'm muting us, sir.
Mic. Oh, are you hearing me?
yes, sir.
All right. Right, so when we apply a stress, we're talking about changing the concentration, changing the pressure, and changing the temperature. So those are the three stress that we can apply. Right, just give me a second. Let me just reply to this person. All right. So concentration. Let us just put a reaction AB, AB react to give C plus B. And just please make a note, solid and liquids, omit them. When we are dealing with equilibrium, solid and liquid. Give me a second, sorry about this. All right, so I'm going to make this a gas, this a solid, and these two aqueous. All right, make a note, solid and liquid, they do not affect your position of equilibrium. So if you change the amount, it's only for gases and things that are aqueous. Likewise, when you are going to write your equilibrium expression, it should only involve reactant and products that are in the aqueous state or the gaseous state. All right. How does concentration affect equilibrium? All right. This is our reaction. We can do two things to the concentration. All right. So remember, we said that we are going to apply. Someone might let me use that person. So remember, we said no, we are going to apply a stress to the system at equilibrium, and the system is going to counteract it. Counteract means that whatever you do to this system, it is going to do the opposite. So if the stress is to decrease the concentration of A, what will be the counteraction?
Repeat that again.
If the stress that we apply to the system is to decrease the concentration of A, what will be the counter-reaction to,
So A will increase.
Yeah.
all right, that is correct. Increase the concentration of A. So remember, let us just get this clear so we don't get any confusion. We are going to apply a stress to the system at equilibrium, and the system is going to counteract it. So we apply the stress, and the system is going to counteract it. And remember the three stresses that we are talking about: changes in concentration, changes in temperature, and changes in pressure. The first one we are looking at is the change in concentration. So if you decrease the concentration of A, then the counteraction to that would be to increase the concentration of A. So whatever we do to the system, the opposite is going to be done by the system. All right? So the question is, if we decrease the concentration of A and the system wants to increase the concentration of A, let me just level up your left and right. The system objective is to increase the concentration of A. Which side of our equation has A?
The left side. The left.
The left side. So if you want to increase A, the equilibrium needs to shift where?
To the left.
To the left.
To the left. And I'm going to make a note again. What should I put this? All right. Decide that the equilibrium shifts to will So what I'm saying here, the side that the equilibrium shifts to will have an increase. So I'm just pointing out that if the equilibrium shifts to the left, whatever is on the left will increase. If it shifts to the right, whatever is on the right will increase. Now, if the equilibrium, if it shifts to the left, so wherever it shifts, there will be an increase. That means wherever it is shifting from, what will happen to those?
It will decrease.
Right. So wherever it is shifting to, you will have an increase in those. And where it is coming from, those products will decrease. So if the system wants to increase A, we said that it would have to shift to the side with A. So what will happen to the concentration of C and V as a result?
Yes.
Decrease.
It is going to decrease. That is correct. Right? So the first question was right. If you dig, and these questions, it can ask in different ways, right? But it don't really change much. So for instance, the stress is to decrease the concentration of A. But when you decrease the concentration of A, there are several questions I can ask. So the first question I asked, if you decrease the concentration of A, in which direction will the equilibrium shift? That was the first question.
To the left.
And it will shift to the left. The second question I asked is what would happen to the concentration of C and B? The answer was it would
They remain the same.
no, It can't remain the
It
same.
would decrease, it would decrease.
It will have to decrease. And let me show you why. Let me show you why. I'm going to erase down here. You have to remember, right, that equilibrium reaction at equilibrium, the forward rate is equal to the reverse rate, right? Now, if you remember from rates of reaction, the higher the concentration, the faster the rate, right? So if you decrease the amount of A, so let's just put a container here, right? And the next one here. And you have 4A, and over here, you have 4B as well. At this point, the rate is equal. If you decrease the amount of A to just 1, would the rate still be equal?
Okay.
No.
No, sir.
All right. Which one of them would have a faster rate?
But I say
Is it A to B? All right. Is it the reaction A to B or B to A? Which one would have the faster rate?
A to B.
No, at this point, look, A, you only have one molecule of A.
yeah, but that's a B to A.
Over here, you have 4 molecules of B. So clearly, if you have more molecules of B, they would collide faster and have a faster rate.
Collision theory.
Right. So going from B to A would be faster than going from A to B. Now bear in mind, what I'm explaining is why the concentration of C and B is going to decrease when the equilibrium shifts to the left. So this is where, right, we decrease the amount of A. So now, because we have more of B, B is going to produce A at a much faster rate than A can produce B. So what is going to happen? You will use up a lot of B and form A because B is forming A quicker than A can produce B. So what you'll notice happened here, did the concentration of B stay the same?
It decreased.
It decreased because you have more particles of B. So B is going to produce A quicker than A can produce B.
Oh, because it shift to the left, that's why it's like it takes some from it.
And the reason why it is shifted to the left, right? When we say shift to the left because it has a faster rate. So because going from B to A, which is going to the left, this reaction has a faster rate. So if the rate is faster in this direction, remember, we are not at equilibrium getting up. We have interrupted it. So we have more of B and less of A. So because B has a much faster rate, then B is producing A much faster than A is producing B. So that is why, this is why we say that the reaction would favor the left-hand side. Because they have more of B, that means B can produce A quicker than A can produce B. So it would appear that the reaction is favoring this side with A because they have more of B. So B is having a faster rate. So it can produce more of A than A can produce B. So you would notice that the amount of A you have is increasing and the amount of B you have is decreasing. And that is why we would say that the reaction now is favoring A. But the truth of it is that because you decrease the amount of A you have, then naturally B is going to produce A faster than A can produce B. And so that is why we say the system favors the left-hand side. More B, faster rate. So you're going in this direction. Is that clear? And because we are going in this direction, remember I said it, wherever the equilibrium shifts, the amount of products and or the amount of molecules on that side would increase. And we are going from B to A. So you notice the amount of A you have, it increased, and the amount of B you have, it decreased. The reason why I'm pointing this out, students tend to get it mixed up after a while. So just remember, wherever the equilibrium shifts, the molecules on that side is going to increase. Wherever it is coming from, the molecules on that side will decrease. It is coming from B, so B decrease. It is going to A, so A increase. I shouldn't have been using B here. Should have used B. Sorry about that. Because A and B is on the same side. All right, so let's use A to B and B to A. So the amount on this side will decrease, and the amount on the left-hand side will increase. All right. Let's do a next scenario. Let me add this stress again. So the stress this time, we are going to decrease. Let me not decrease this time. Let me increase the concentration of A. What is going to be the counteraction?
It's like a decrease, the concentration.
Yeah, the decrease, yeah.
All right. Now, if we're not decreasing A, the system is going to decrease A. Remember, the system, it only has two options, favor the left or favor the right. If it wants to decrease the concentration of A, will it go left or right?
Right.
That is correct. Because anywhere the equilibrium shifts, the amount of molecules on that side is going to increase. And where it is shifting from, the amount of molecules on that side will decrease. So if the system wants to decrease the concentration of A, it will shift to the left. All right. If we increase the concentration of A, what will happen to the concentration of C?
C concentration will increase.
That is correct. So the concentration of C, it will increase. That is good. All right. Let me put it this way now. This is your reaction, right? If you want to improve the amount of products that you're getting, so let me use the term yield. If you want to increase the yield, why are you? YEILD or YIELD?
Yeah, man, that good, man.
That right, so that's
Increase the yield of the products. So tell me two things that you can do to increase the yield of the products. Just by using concentration, two things that you can do to the concentration of either reactants or products to increase the yield of the products.
You would decrease
So
the
I can increase the reactants
no decrease the concentration of reactants.
Or
All right,
decrease.
let me just show you.
So increase the concentration of the reactant and you don't get this.
I
So
can
we here decrease concentration of reactants. We here increase the concentration of reactants as well. What else can we do?
so we can
Decrease the
decrease the
concentration of
products.
the products. Yeah.
All right, and we here decrease concentration of the product. And I'm sure we all know that square bracket means concentration, right?
Yes, sir.
So the objective is to increase the amount of B. What you have to remember now, the system is going to do the opposite of what you want. So let us start with decreasing the concentration of the reactants. So what you can do to know if your answer is correct, just set it, just write back stress and write counteraction. All right? You're saying that if we want to increase the products, we should decrease the concentration of the reactants. If you decrease the concentration of the reactants, that is the stress that you're applying. What would be the counteraction to this?
the system will increase it.
Increase it.
The system is going to increase the concentration of the reactants. Right? So decrease the concentration of the reactants, the system is going to do the opposite. So what you need to bear in mind, right? If you have a particular objective, you have to ensure that when the system does the opposite of what you did, it works in your favor. What I mean by that now, let us look at this part. If you increase the concentration of the reactants, how will this system counter it?
It's going to decrease the concentration.
It is going to decrease, so two things, all right? So it will decrease the concentration of the reactants, right? What else it will do?
Increase the
The concentration of the product.
Right, which is what we are interested in. So it will increase the concentration of the products. That is correct. So you have to ensure that whatever stress that you apply, when this system counteracts it, it works in your favor. In the first instance, when we decrease the concentration of the reactants, it is going to counteract by increasing the concentration of the reactants, which means that what will happen to the concentration of the products? If the system is increasing the concentration of the reactants, what is going to happen?
It will decrease.
It will decrease, that is correct. Because to increase reactants, you have to use up your products. To increase products, you have to use up the reactants. Right? So the concentration of the products will decrease. And that is not what we want. Right? Let me just separate these. So if you decrease the concentration of the reactants, the system will increase the concentration of the reactants and decrease the concentration of the product. But if you increase the concentration of the reactant, the system is going to decrease the concentration of it and increase the concentration of the product. The next one now, what will happen if we decrease the concentration of the product?
Will increase the
That is correct. So if we decrease concentration of the product, and when we say decrease it, so like in the Haber process, at a certain point, the ammonia that is produced, some of it is removed. And so this equilibrium will always be shifting to produce more ammonia. So if you decrease the product, the system is going to increase the concentration of your product. Right? So in this scenario, other than just say what will happen if you decrease the concentration of this, of the reactant or product, they can ask you if you want to achieve a particular objective, what will you do? Which is what we did in this scenario. If you want to increase the amount of products, you would increase, so this one is correct, and this one is correct. You would increase the concentration of the reactants or decrease the concentration of the products. All right. Now let's move on to pressure. So this one was with concentration. We're going to move on now to see how pressure affects equilibrium. When it comes to pressure, fewer moles, just remember this statement. Fewer moles equals lower pressure. Right? And more moles equal higher pressure. So to decrease pressure, so before I even ask any question, fewer moles will result in lower pressure, more moles will result in a higher pressure. So if the system wants to decrease the pressure, so if it wants a lower pressure, it would have to favor the side with fewer moles. And if it wants to increase the pressure, right? If it wants a higher pressure, it will have to favor the side with more moles. So when it comes to pressure, we're going to pay attention to the equation, right? And look at the amount of moles that is present on both sides of our equation. So for this equation, how many moles of gases do we have on the reactant side?
4.
That's correct. So 4 moles in total. And how many do we have on the product side?
3.
3.
All right. So let me just erase this. So which side of the equation would cause the pressure to increase?
The right-hand side.
No, as in which side of a higher pressure?
Left-hand side.
Left.
All right. So over here as the higher pressure. So if you ever, can someone explain what concentration? All right, so when I'm finished, I will recap that. All right, so higher pressure, if the system ever needs to increase the pressure, over here, it will shift to this side. So higher pressure will result in an increase in pressure. All right. So if the system needs to increase the pressure, over here is where it will go. This side has fewer moles, so it has a lower pressure. So if the system wants to decrease the pressure, it will have to shift to this side. So what I'm going to alter, all right, let me start with one of them first. If I want to increase not that one. All right, what will happen if I decrease? What will happen if I decrease the pressure? Oh, and with pressure and temperature, it's different from concentration in that when you're adjusting pressure and temperature, it's not like you can say I am adjusting the pressure for A, B, or C. The reaction is taking place in a container, right? In a vessel. You can only change the pressure of the vessel. So A, B, and C, all of them are in the vessel. You can change the temperature and pressure of the vessel. It's not like concentration where you can change the concentration of A, B, or C. You just change the pressure of the overall reaction, right? So what will happen? So only 2 scenarios are: increase the pressure or decrease the pressure. So if the pressure is decreased, if we decrease the pressure, right, what will happen to the concentration of A? How will it affect the concentration of A? And how will it affect the concentration of C? So when we decrease the pressure, what will happen to the concentration of A and to the concentration of C? Before you answer, the first thing you need to do, determine where the equilibrium will shift. So before you answer this, determine where the equilibrium will shift. Because remember, wherever it shifts to, anything on that side is going to increase. So if we decrease the pressure, what will be the counteraction to a decrease in pressure?
An increase in pressure.
All right. Now, which side will result in an increase in pressure.
Side with
The
more
left.
moles, the left.
Okay.
Right. So if the equilibrium shifts to the left, equilibrium shift left, that means it is shifting to this side, right? So what will happen to the molecules on this side?
Increase.
Increase.
Increase in concentration.
Right. So the concentration of A is going to increase, right? The concentration of A, it will increase because it is shifting to the left hand side. So what will happen to the concentration of C?
Increases.
It will,
Decrease.
that is correct. So the concentration of C will decrease. All right. So when they ask you the question, just determine which side the equilibrium will shift to, and that's it. Because you know that once it shifts to the left side, oh,
So I have a question, if I may ask.
go ahead and ask the question.
I thought when it comes to pressure, pressure increases to the side which have the least amount of moles.
No.
Yeah. Uh,
So first, the side with more modes, right? So remember, it's gas. So it's because it's a revision I couldn't get into explaining why the more modes will equal to higher pressure. But if you have more moles of gas, they would exert a greater force on the container, a greater pressure on the walls of the container. So when you have more gas, when you have more gases present, the container would receive a greater amount of pressure. Because remember, they are always colliding. So let me just draw a diagram, right? If you have one molecule of gas molecule here, bouncing around in the container, versus this, in which container do you think a greater force is it being exerted? Or which one do you think?
The second one, got the collisions.
Right. So if these are gas molecules, then this container would have a higher pressure than the one with only one molecule present inside of it. Is that any clearer? For the person that was asking?
yes, sir.
So it's the same here. This one, the side with more moles, if you were looking at it in terms of the reaction, it would exert a greater pressure. All right. So that is why the system will counteract whatever we do by favoring one of these two. Right? Because what happens, let me just show you quickly. If we increase the pressure, right, and the system wants to decrease it, it would favor this reaction over on this side. Because you realize that this reaction, it would produce less molecules.
I'm grateful for this job and I'm grateful for this woman.
You realize that this container has less molecules, right? So it has a lower pressure. So if the system needs to lower the pressure, then it will have to favor this one, because this one has a lot of molecules, which will cause the pressure to increase. So by favoring this reaction, it will be using up molecules from this side, which would see the pressure decreasing. All right? So that is why we say that the side with more moles will have a higher pressure, and the side with lower moles will have a lower pressure. So if the system wants the pressure to increase, the equilibrium will have to favor the side with more moles on it. because more moles, higher pressure. Pressure will go up. All right? We can do the
Sir.
reverse. Yes.
So if
Sir.
you, all right, so you increase the pressure, it now go shift to the side with the 3 moles.
That is correct.
Okay.
Yeah, man. Because the 3 moles, what we're doing now is, so let me just put 4 here and 3 here. So let's say this diagram, this diagram would represent the, let's say this is representing the 4 moles and this one is representing the 3 moles. All right. We know that this container has a lower pressure, this one has a higher pressure. So if you want the pressure, right, to increase, would you favor this container or this one? Which one do you think would make pressure increase? This one or this one?
The one with the more money.
Or
The one with the more molecules inside of it, right? 3.
Yes, sir.
What was the question? No, I was just trying to make this point clear about the 4 moles and the 3 moles. I was saying that I am using this diagram here. Let me just clear it from off the board. Let me just label this A. No, let me use 2 separate letters, S and P. We all agree that P has the higher pressure, right? Comparing S and P, we all agree that P has more molecules, right? So it would have higher pressure, right? And this would have the lower pressure. So let us just say you are this system, right? And something happens. If you want the pressure to go up, which of these would you pick? S or P?
P.
If you want the pressure to increase.
P, sir.
That is correct. Right. And if you want the pressure to decrease, all right, somebody says Y. So if you want the pressure to go up, all right, somebody answer them already. So remember, more molecules, higher pressure. So now, if you want the pressure to decrease, which of these would you favor? SRP.
S.
Right.
S.
So let me just put 2 arrows here now. All right? One going from S to P and one going from P to S. This is an equilibrium reaction taking place, right? And let me just open it. All right? Let's say we are at equilibrium, and then boom, the pressure on this system. So let us put on a button on the container, right? To adjust the pressure of the system. So let us say we adjust the pressure on the system, we decrease it. So let us say we jump the pressure from 100 to 50, right? What will happen now? If we decrease the pressure, the system wants to increase it, right? So which of these SRP, which one will it favor?
P.
P. And so if it favors P, the equilibrium is going to be favoring P. So it is going to shift to the right hand side. And what will happen now? The reverse. If pressure increases, let's say from 100 to 200, what will the system do?
Decrease it.
decrease it. Look at the two containers, which one have which one have more molecules present, S or P?
P.
P.
So can we shift to P if we want the pressure to decrease?
No.
No, sir.
No.
We have to come over to S, right? So when I say 4 moles and 3 moles, that is exactly what is happening. So just imagine S is the 3 moles and P is the 4 moles, right? Whenever we want the pressure to go up, we have to favor the side with more moles. And whenever the pressure needs to go down, it shifts to the side with fewer moles. That is just it. All right? So that's all you need to remember. You want the pressure to go up, you have to, the equilibrium has to shift to the side with more moles. And if you want it to decrease, it has to go to the side with fewer moles. All right? Let me put an actual reaction on the board and ask a question. If the question says state, do not offer an explanation. If it says state, just state the answer. Do not say this will happen because of so and so. Once it says state, do not offer any explanation. So using pressure, state. So just state if you would increase the pressure or decrease the pressure. When it says explain now, then you will tell what will happen when you increase or decrease the pressure. So using pressure, state how the yield of SO3 can be increased with tools, supposed to have two there. I'll give you 2 minutes to think about your answer. All right, somebody said increase the pressure of the reactants. So let me just remind you again, you cannot, when it comes to pressure, it's not like concentration where you can increase pressure of reactant or product. All of them would be in the one container. So SO2, O2, and SO3. Remember, equilibrium reactions take place in a closed system. So when it comes to pressure, you are changing the pressure of the entire system, not of a reactant or a product. All right, so you would just say increase the pressure or decrease the pressure. All right, let me see some answers. Okay. All right, so I see decreased pressure and I also see increased pressure. See it increase again. All right, so let us see. So first, which of these sides, left or right, which one has more moles? Left side or the right side?
Right.
Let's
Right.
Left.
Oh Lord, left.
How
The
many
left
moles?
side.
How many moles are on the left hand side?
3.
3.
3.
And how many moles are on the right side?
2.
2.
So which side would cause the pressure to increase?
The left. The left.
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 So the left has more moles, and once it has more moles, the system will favor it whenever the pressure needs to increase. This side has fewer moles, so when the pressure needs to decrease, the system will favor this side. All right. So before you answer the question, look which one has more moles and look which one has fewer moles. Then pay attention to the question now. We are trying to increase the yield of SO3. So if we are trying to increase the yield of SO3, where do we need the equilibrium to shift? To the right or to the left?
To the right.
That is correct. So we are trying to increase SO3. That means equilibrium must shift to the right. So based on this, right, if it is shifting to the right, what is the system trying to do?
Decrease the pressure.
Right? In shifting to the right, so whenever the system shifts to the right, based on our equation, we see that the right-hand side has fewer moles. So if the system is going to shift to the right, that means it would be trying to decrease the pressure. Now, under what circumstances will the system try to decrease the pressure?
If you increase it.
Exactly. So the only time the system would be trying to decrease the pressure is if we increase the pressure. And so that is what we would do. We would have to increase the pressure. All right, so it says, state how the yield of SO3 can be increased. So the yield can be increased by increasing the pressure. All right, that's how we state it, right? We state it, increase the pressure, the yield will increase. Now we must offer an explanation. So why, when we increase the pressure, how would that result in an increase in the yield of SO3? Anybody want to offer an explanation? What would happen? So all you need to do is tell where the equilibrium will shift and what happens as a result. All right, so if the pressure is increased, or when the pressure is increased,
Like everybody lost, sir.
Sir.
yeah.
Sir, I'm confused.
If you're confused, I can ask
Sir. When you
Yeah.
increase the pressure, the
Yeah.
system I go shift to the
side
side
with
with
the
the
more-
SO3 with the
Yeah.
less moles,
Right.
with the less gas molecules.
That is correct.
So I'm still confused.
All right. So, all right, not a problem. If you don't understand, just talk up so we can
So with the
explain.
question. So
Yeah,
with the
man.
question, not the
Sure.
pressure when you decrease the pressure, the equilibrium of a shift to the side with fewer moles.
Repeat
No,
question.
before.
Sir,
Just, yeah. No, man.
Sir,
Go ahead.
Sir, if you decrease the pressure, the equilibrium of a shift to the side with the fewer moles, and if you
No,
increase the
man.
pressure,
Wait.
if you shift to the side with the more moles.
Wait. So, if you decrease the pressure, they are saying it will shift to the side with fewer moles. Is that what you're saying? Just want to get
So
it.
that may I ask.
All right. So remember, no, it could not shift to the side with fewer moles. I'm going to tell you why, right? So remember, the side with fewer moles, it would have a lower pressure. So if you decrease the pressure, so let us go back to doing the stress and the counteraction. If you decrease the pressure, the system wants to increase the pressure, right? When you compare both sides of the equation, and I also saw someone ask how we got the 3 moles on the left-hand side. So we're looking at the balanced equation, and we have two moles of SO2 and 1 moles of oxygen. So that's a total of 3 moles. All right, so it's 2 SO2 and 1 O2, so the total is 3. And over here, we only have 2 moles of SO3. So we said that the side that has more moles, right? That side, let's not think about that side, because probably we'll have to say that. But what I wanted to visualize, let's go to visualizing again. This side has more moles. So if you're looking at it from a diagram perspective, right? This container would have a higher pressure than this one. 2 things are going to happen at each time. Either you decrease the pressure or increase it. When you decrease the pressure, right, the system is going to do the opposite. That is the whole basis of the Chatler's principle. A system counteracting whatever someone does to it. So if you know that, let's put yourself as this system, right? You are at equilibrium, and then the pressure was decreased. You have 2 options. One of these 2 options, right? This side with 3 moles has higher pressure, right? It has a higher pressure. This side with 2 moles, it has lower pressure. Now, if you are the system and you were at equilibrium and the pressure was decreased, and you want the pressure to go back up, which of these scenarios would you favor? The one with lower moles or the one with more moles? Which one would you favor?
More.
Hmm?
More moles.
More.
Side with more moles, right? Because you know that if you favor the side with more moles, what is going to happen to the pressure?
Will increase.
Exactly. Now, let's do it again now. Again, you're in this system, right? You were at equilibrium. The pressure suddenly increases. Which of these would you favor? So remember now, you are at equilibrium. The pressure is suddenly increased. To get back at equilibrium, you need to bring the pressure down. So if you need to bring the pressure down, which of these will you favor? The one with fewer moles or the one with more moles?
Fewer moles.
Fewer moles.
That is correct. Because the one with fewer moles exerts a lower pressure. All right. Now let's look at our equation. We are trying to increase the amount of SO3 that we are getting. In order to increase it, right? So this is an equilibrium reaction. Everything, so it's at equilibrium. What we want to do now is switch up the equilibrium and make the reaction favor the product side. So it's at equilibrium, but we don't want it at equilibrium. We want more of SO3 to be produced. So if we want more of SO3 to be produced, right, we need to ensure that the equilibrium is favoring this side with what? Fewer moles, right? Because if you notice, this side has 2 moles, over here has 3 moles. So if we need this equilibrium to favor the side, to shift to the side with fewer moles, which one of the circumstances, right? You chose fewer moles. In which circumstance? When the pressure was increased or decreased? Wait.
Increased, sir.
All right.
Decrease.
Wait, let me say, because I think what is happening, you're mixing up both the stress and the counteraction. So if the stress is increasing the pressure, then the counteraction is lowering the pressure. So you have to try and focus on the counteraction. So if you hear increased pressure, don't just automatically say more moles. So look at what the stress is, and then what the counteraction would be, and make the decision based on the counteraction. So,
Excuse
if
me,
you-
sir.
yes,
Sorry for this. So basically, what you're saying that for this one, if
Mhm.
if you decrease the pressure over the, is it the left side with the 3 moles? If you
wait,
decrease the pressure there.
no, wait, let's see that question. You cannot, you're saying that if I decrease the pressure with the 3 moles, I'm telling you that don't do it like that. You only do it for concentration. Pressure, remember that it's a reaction. So it's not like I can decrease the pressure of a molecule. You can, yeah, you're decreasing the pressure of the, it's just like imagine you're baking, right? And you put so you mix up the ingredients and all of that and put it in the oven. What you're saying that, right? It's like if I can decrease the pressure or the temperature of a particular ingredient. Is that possible?
Excuse me, sir. So I have a question.
Yes.
How are there 3 moles on the right, but 2, are there 2 moles on the right, but 3 on the left?
All right. So this is the 2 moles of SO2, right?
Yes, sir.
And we have 1 mole of oxygen. So we're adding the moles. So 2 from SO2 and 1 mole of oxygen. That's a total of 3 moles.
Okay, sir. Thank you.
So it's the number of moles on the reactant side versus the number of moles on the product side. So
Okay.
Excuse, sir.
go ahead.
So what will be the so the stress in this equation will be the increased pressure?
If the stress would be to increase the pressure,
Yes, sir.
yes, based on this scenario, you would have to increase the pressure. And how you know that, right? You have to look at what you are trying to achieve. You are trying to achieve more SO3, which means that the equilibrium needs to shift to the side with SO3. SO3, the side with SO3 has fewer moles. That means when the system is favoring SO3, it is favoring a side with fewer moles. So the pressure is going to decrease whenever it is favoring SO3. So if you need the system to favor SO3, you have to increase the pressure. Because
So and the
when you,
decrease in, oh sorry, but so the decrease in pressure will be the counteraction.
right. So you have to, right. So you have to ensure that when this, whatever this system is countering, it is going to work in your favor. So when you increase the pressure, the counter to that would be to decrease it, right?
Yes, sir.
Right. And when, so that decrease, where will the equilibrium shift? To the right or to the left?
To the right.
That is correct. And so that is how you know that you should increase the pressure, because this is your explanation now. If you increase the pressure, the system is going to do what? Counter it, right?
Yes, sir.
And it is going to counter it by doing what?
Decreasing the pressure.
Right. And in order to decrease the pressure, it has to shift to the side with the fewer moles, right?
moles.
Exactly.
Yes, sir.
And in this case, the side with fewer moles is the product,
SO3.
right?
Okay, yes, sir. Understood.
Yeah, man. So that's what happens. All right, so let us move on to temperature. All right. Now for temperature, we have two types. When I did energetics, right? We have two types of reaction in terms of heat change. Two E words.
Exothermic and endothermic.
Right. So when we're dealing with temperature, repeat explanation, please. All right, I'm going to do temperature and then come back. All right. Let me just try again. So when you're dealing with pressure, let me just do it again. When you're dealing with pressure, right, you're going to get a balanced equation. You're going to look at the reactant side, everything that is on it. All right, so let me just do this. And it don't have to be two products, all right? It can be just a single reactant. So let's say I have 2A, and I'm going to put two products on this side, B plus C, all right? So you're going to get a balanced equation. You're going to add up the number of moles on each side. So we have 2 moles over here and 5 moles over here. 2 moles of B plus 3 moles of C, that's 5 moles. Then now we are going to label it, right? This is just so you don't make any mistake. Whichever number is lower, you just put lower pressure, right? The one with more moles, you put higher pressure. And let me just add this as well. You see where you put lower pressure, just write equilibrium shifts here, equilibrium shifts here to decrease pressure. On the side with more moles, they put equilibrium shifts here to increase pressure. So you get your balanced equation, you look at the moles, compare them, lower pressure, higher pressure. All right. So the equilibrium will shift to this side with, let me put, so this side has the fewer moles, and this one has more moles. So the question is, right, based on this example and what I have written here, when will the equilibrium shift to the right-hand side? Based on this example, when will it shift to the right-hand side? When you do what? What will you do that will cause the equilibrium to shift to this side?
Decrease the pressure.
Decrease the pressure.
Decrease the pressure.
All right, and everybody agree with this? Right, good. Because when we decrease the pressure, the system is going to do what?
Increase the pressure.
Exactly.
Increase.
And so it has to shift to the side with more moles. Good, wonderful, right? And that's basically. Now, what would happen to the amount of A? So what will happen to the concentration of A if you increase pressure? If you increase pressure, how will that affect the amount of A?
It would increase.
Decrease.
It will, all right. So you see,
Increase.
all right, so you see when I ask a question like, when you increase the pressure, what will happen to A? Don't just give, in order to be on the safe side, right? Just go through a series of answers. The first thing I need to answer, if you increase the pressure, how will the system counter it? So you increase pressure, what will the system do?
Decrease the pressure.
All right, that's the first point. So if the system wants to decrease the pressure, where will it shift? Left or right?
It
Left.
will shift to the
Left.
side with the more gas
Fewer
molecules.
So did someone just say it will shift to the side with more?
Yes, sir.
All right, hold on. So we increase the pressure and we said the system is going to decrease it, right? If the system wants to decrease the pressure, what will it do?
Shift to the side with fewer particles.
Right. Don't forget that here, the side with fewer moles has less pressure. So when the system wants to decrease it, it shifts to the side with fewer moles. All right, so that's the second part. And the third part now, we answer the question. So we said the system is going to decrease it, and so it has to shift to the left. So when it shifts to the left, what will happen to the amount of A?
Would increase.
Going to decrease.
Increase.
It is going to
I'm
increase.
confused.
Were you here from the start? Just to check.
Yes, sir.
All right, if we're here from the start, remember we said that anywhere the equilibrium shift, what will happen to the amount of molecules on that side? It is going to increase. So just make a note of it now if you didn't. Wherever the equilibrium shifts to, whichever side it shifts to, the amount of molecules on that side or the concentration on that side it is going to increase. Anywhere equilibrium shift to, the molecules on that side, it is going to increase. That is why when it shifts to the left, we know that the amount of A is going to increase. Because if the equilibrium is shifting to that side, it means that side is being favored. So it is going to increase. So as a caution, when you get a question like this, just go through the different steps. First, look at how the system is going to counter it. Once you know how the system is going to counter it, look at where the equilibrium is going to shift. And once you know where the equilibrium is shifting to, you know how the concentration will be affected. All right. And the last one, to see if we grasp it, if you decrease the pressure, right, how will it affect the concentration of A? Go through the 3 stages. If you decrease the pressure on the system, how will that affect the concentration of A? First, tell me the counteraction.
First, it will
The pressure is going
increase.
to increase.
All right. So to increase it, the equilibrium is going to shift to which side?
The right.
Right.
Because there on the right side we have more
More
moles, right?
Molecules.
Good.
Yeah.
Right. So when it shifts to the right hand side, what will happen to the molecules on the right?
They will increase.
And what will happen to the molecules on the left?
They will decrease.
That is correct. So if you decrease pressure, the amount of A is going to decrease. And what we have just done is explain it as well. So if they ask you to state and explain, we just did the explanation. So stating would be that the amount of A would decrease. The explanation we did was that the system would counter the decrease in pressure by wanting to increase it. And so it would shift to the side with more moles, which is the right hand side. And as a result, the concentration of the products will increase and the concentration of the reactants will decrease. All right. Let's do temperature now. So for temperature, you are going to get the reaction just like this, and you are going to be given a sign. So the delta H, and you will see negative, and let's say you will see either negative to indicate exothermic or positive to indicate endothermic. So let's say this reaction is negative 450, right? Kilojoules per mole. So when you get the reaction and they're asking about temperature, the first thing you need to do is pay attention to the sign to see if it is exothermic or endothermic. All right. Whatever sign is given, that is for the forward reaction. Whatever sign is given for delta H, that is for the forward reaction. The reverse reaction is the opposite. So in this case, the forward reaction is exothermic. All right? If the forward reaction is exothermic, in exothermic reactions, what happens to temperature of this system? Does it increase or decrease?
Increase.
Increases.
Okay. So temperature increase. So, under what circumstances will the system favor the forward reaction when it wants to achieve what exactly? The forward reaction is exothermic, therefore it causes temperature to increase. Oh, so when we're dealing with temperature, again, it's two things. Either increase it or decrease it. So under what circumstance would a counter reaction be to increase the temperature?
A decrease in temperature.
All right. Yes, that is correct. So the system is going to favor this reaction when the temperature decreases. So this system favors this reaction when the temperature decreases. All right. And the opposite now is going to be for the reverse reaction. So the reverse, if the forward is exothermic, the reverse reaction is endothermic. And so if the reaction is endothermic, the temperature will do what?
Decrease.
Decrease.
That is correct. So when will this, under what circumstance will the system favor this reaction?
When the
Increase in
temperature
temperature.
increases.
Exactly. All right, so when you get the equation, look what you have. The sign is always for the forward reaction. So in our example, when sulfur trioxide is being produced, heat is given off. That means the temperature of the reaction increases. So let us look at the question, all right? Using temperature, all right, before you look at the question, if the system wants to produce, if the system wants the equilibrium to shift to the right-hand side, will it cause the temperature to increase or decrease? What is it? Increase,
Decrease.
right? Because when you produce SO3, the temperature is going to increase. And when you produce SO2 and O2, the temperature is being what? Decrease.
Decrease.
Right. Just remember, this system, it can increase and decrease the temperature. And so can you. That is why, to not get them confused, we have to focus on the counteraction, which is what this system is doing. So question, if we want the yield of SO3 to increase, where does the equilibrium need to shift?
To the right.
To the right, good. So if it is going to shift to the right, what kind of reaction is taking place?
Exothermic.
Exothermic. So if the system is favoring an exothermic reaction, right? What would it be countering?
A decrease in
A decrease.
Exactly. Wonderful. So the system, the equilibrium shifts to the right because the system is favoring the right hand side. And if it is favoring the right-hand side, it is favoring the exothermic reaction, which is an increase in temperature. And the only reason it would be favoring an increase in temperature is because we would have decreased it. All right? Let me go again. Somebody asked me to repeat. So the question is, how could we increase the yield of SO3? Remember, take the answer in stages, right? So the objective is to increase the yield of SO3. That means we need the equilibrium to shift to the right-hand side. If the equilibrium is shifting to the right-hand side, which is the forward reaction, we know that the forward reaction is exothermic, which means that the temperature is being increased. So the system is favoring an increase in the temperature. If the system is favoring an increase, it had to be countering the opposite. So that means we would have decreased the temperature. And so now the system is doing the opposite by increasing it. And it increases it by favoring the exothermic reaction, because when the reaction is exothermic, heat is given off, which means the temperature will go up. So to increase the yield of SO3, we have to decrease the temperature, because the system is going to counter that by increasing it. And the side that increases the temperature is the right-hand side. Because when SO3 is being produced, the temperature increases. All right. I'm going to erase this and we do our next example. What you can do, right? Once you spot the delta H, so delta H was negative, right? You can label the equation. So over here is endothermic, and over here is exothermic. And if it's endothermic, that means the temperature will decrease. And on this side, the temperature will increase. And if you set it up like that, right, these are the options that the system has. It can counter an increase in temperature by shifting to the left, because when it shifts to the left, the temperature will decrease. And it can counter a decrease in temperature by shifting to the right, because when it does that, the temperature will increase. So the question I'm going to ask you, what will happen to the yield? All right. So what will happen to the yield of SO3 if the temperature of the system is increased? So what happens if temperature is increased? Take it in stages. First thing you must answer, if you increase the temperature, what will this system do?
Decrease it.
The temperature
Decrease.
of the system.
So if it is to decrease the temperature, which side will it will it shift to?
The
Right.
external.
Left side.
Right. Good, which is the left-hand side. So if it shifts to the left, what will happen to the amount of reactants?
It would
Will
increase.
increase.
Correct. And what will happen to the products?
It will decrease.
Decrease.
Will decrease. Wonderful. All right. And that's all your answer. So just take it in stages. Now, if you're answering this question, you wouldn't write all of that. You would just go through the process and then your final answer, because it just say what will happen. It didn't ask you for an explanation. So you just need to say the concentration of or the yield of SO3 will decrease. If they ask you for an explanation now, that is when you would explain all of that. All right. So those are the three stresses that we look at for the Chatterjee's principle. All right, so now it's time to perform some calculations with Casey. All right. So I'm going to put some on the board now. As soon as you are finished writing, I will go through the calculation. Right, is anybody still writing? And so for this one, what would have been the equilibrium expression? KC. What would be the expression for KC?
The concentration of the products over the concentration of the reactants.
It's NOCl. And what happens to the two?
It squares it.
Divided by NO squared Cl2. And so all we do is plug in these numbers into the equation. And so it would be 0.06 squared divided by 0.14. And that would be your answer. Now for equilibrium, we also have to work out the unit. So as soon as you finish writing, we are going to calculate the units.
Excuse me, sir.
Go ahead.
Isn't the answer 0.644 and not 664?
Let me check.
0.64.
64, progress it. This is 0.64.
44.
All right. All right, so is anybody else writing? I can work on the units now. All right. So it was, right, so it was NO Cl squared divided by NO squared Cl. Now, we know that the units for concentration is moles per VMQ. Now, there's a short way of doing it, but I'm going to go through it stepwise in case anybody doesn't get it right. So I'm just going to go through in details. So the concentration, the unit for concentration is moles per VMQ. And up here we square it, right? That means it is moles per VMQ times moles per VMQ. That is for the numerator. divided by NO squared. So again, it's moles per dm cube times moles per dm cube. And we have Cl, so it's moles per dm cube, right? So remember now, when in division, we're going to change it to multiplication and flip everything on this side. So it's moles per dm cube times moles per dm cube times flip everything dm cube divided by mole dm cube divided by mole dm cube divided by mole. So mole cancel mole, dm cube cancel dm cube cancel dm cube, mole cancel mole. And so the answer is dm cube per mole. All right. Now what you can do, if you notice, so the numerator is square, right? And this denominator is squared as well. So in terms of the units, they would have cancelled out. And so what you would have left with, it's just this moles per dm cube, but it's a denominator, right? So if you remember, it will just flip and become dm cube per mole. But make sure I went through it in detail, so if anybody doesn't understand, this is how we would arrive at BMQ per mole. Right? And always work out the units for KC. Right? So that is how we arrive at it. All right, this type of question, this one is straightforward, right? Because they already give us the concentrations for everything at equilibrium. I'm going to give you one now where we don't get all the concentrations at equilibrium and see how it's done. Is anybody writing, by the way, before I finish? I see someone mentioning unstable. They're correct. Is anybody writing? All right. So, all right. Let me know when you're finished.
So you can erase now.
All right. All right. So before I erase, right? So it says we have our equilibrium. We have our equilibrium reaction, right? It says when 4 mole of hydrogen iodide are placed in 5 BMQ in a 5 BMQ flask at 458 degrees Celsius, the equilibrium mixture was found to contain 0.442 moles of I2. So we use 4 moles of HI, 5 BMQ container, and at equilibrium, we have 0.442 moles of I2. Now, in order to calculate Kc, we need the equilibrium concentrations for HI as well as H2. So the first part of finding Kc, we need to find the equilibrium concentration of HI and H2. All right, so I'm just going to shift the equation to here. So at the start of the reaction, right? So the initial stages, we used 4 moles of HI. Now at the start, we could not have any products as yet, right? Because the reaction hasn't started yet. So it's the initial, we have over 4 moles of HI, and we don't have any moles as yet. Now, as the reaction progresses, there will be a change, right? The reactant is going to decrease and the product is going to increase. Now it is going to increase by an amount, but based on the moles from the balanced equation. So from the balanced equation, we have 1 mole of H2 and 1 mole of I2. So we are going to use X to represent each of them. Now, because it's the products, it is going to increase over time. All right? And because this is the reactant, it will decrease over time. Now we have 2 moles from the balanced equation, so it will decrease by 2x. Now the question said that
Excuse me, sir.
yes, go ahead.
How did you get the 4 again?
In the question, let me see it. It says, in the question, it says when 4 mole of HI was placed in a 5 dm cube flask. So the hydrogen iodide is the reactant. The I here, it means initial. So when the reaction is about to start. So at the start of the reaction, we use 4 moles of HI, and that's from the question, when 4 moles of hydrogen iodide was placed in a 5 dm cube container.
Yeah, thank you, sir.
Right?
So I have a question, sir.
Yeah, man.
Can't you divide the 4 by 5 dm cube?
Please repeat.
Can't you divide the 4 by 5 dm cube?
Not as yet. And
Pardon?
the reason why, because when we're going to divide by the 5 cm cube, we're finding concentration. But we're not finding concentration at the start. We're going to find the concentration at equilibrium. So we still have something else to find. And so,
Right.
yeah. So, right, so each letter represents something, right? So at the initial stages, we have 4 moles of the reactant and 0 moles of product because the reaction hasn't started yet. It's not really a negative, so it's really 4, it's not negative 2x. It's 4 minus 2x. So where I put the minus to indicate that the reactant is decreasing as the reaction goes on. And the positive here means that it is increasing, right? So the question also said now that at equilibrium, the mixture was found to contain 0.442 moles of I2. So at equilibrium, we have 0.442 moles of I2. All right. Someone asked me to start over, so let us go quickly. So we're trying to calculate Kc, right? Now the formula for Kc is products over reactants. So we'll have the concentration of H2, concentration of I2 divided by the concentration of HI squared. This is an equilibrium reaction. That means we have to use the concentrations at equilibrium. We weren't given, like the previous question before this, we were given the questions of the reactants and products at equilibrium. And so we could go ahead and calculate it. But for this question, they did not give us the concentration at equilibrium for all of these, right? So when that happens, when you don't get the concentration at equilibrium, we have to use what we call the ICE method, right? Which is to set up this table. So let me just erase it and tell you how I got each of these. All right. So I means the product here. No, this is not the product. This is the reactant. It's a decomposition reaction. So the product is done. This is the reactant. These are the product. All right. No, I means at the initial stages. So the question said, at the start of the reaction, we are using 4 moles of HI. This was said in the question. So when the question says that this was added at the start, so the 4 moles, it was added at the start. That is the reactant. That is I. Now, if the reaction hasn't started yet, you cannot get any product because it is the, all right. How do you know when to use the ICE table? Just look for yourself. You don't have the concentration of H2 and HI at equilibrium. So there's no way that you can go ahead and use this equation because we don't have the concentration for H2 or HI at equilibrium. Once you don't have everything at equilibrium, you have to come to the table, right? And figure it out. So this is how we do it. They tell you that there are 4 moles of HI at the start. Reaction hasn't started yet, so you cannot have any products, right? Now, as the reaction progresses, there is going to be a change. The reactant, the amount of reactant you have, it is going to decrease. So the minus means it is going to decrease. The concentration of the product is going to increase. Now, at this point, to represent the reactants and products, we're going to use X, right? Now, you pay attention to your balanced equation. The moles of your reactant and product, you put it in front of X. So, for instance, you have 2 moles of HI, so here you would have 2X. But you only have 1 mole of hydrogen, so it is just X. And you have 1 mole of iodine, so again it is just X. So the hydrogen peroxide concentration is going to decrease by 2X, and these are going to increase by X. What is X? So the question went on to state that at equilibrium, it was found out that we have 0.442 moles of I2 at equilibrium. Now I2 is X. You notice H2 is also X. So if at equilibrium you have 0.442 moles of I2, you must have the same amount of moles as H2 because both of them are just X. So they must be equal. Now, when it comes to...
Sir?
Yes?
Yeah, isn't it 0.142 instead of 0.442?
Sorry. Let me check. 0 point... No, it's 442. Let me see. It's 442. All right, so it's 442, not 142. All right, now for 2x, we said that x is 0.442, right? So that means 2x is 2 times, and so leave this here. At equilibrium, we're going to have 4 minus 2x, and 2x is 2 times 0.442. All right, so we figured out what x was. And remember, initially it's 4 moles, it changes minus 2x. We figured out that x is 0.442. So at equilibrium, the amount of HI that we are going to have is the initial minus the change, which is 2x. And 2x is 2 times 0.442. So it's 4, take away this answer. And you should end up with 3.116. All right. Now, these are not concentration, these are moles. The unit here is moles, so 0.442 mole. Now, what is the unit of concentration?
Moles per decimeter cube.
Right. So if you have moles here and you go ahead and plug this into the equation, it is going to be incorrect. We have to use the concentration at equilibrium. This is just the number of moles at equilibrium. So this is where you complete, or this is where you finish with the ice table. We use this table to get the remaining concentrations at equilibrium. All right. So once we get the number of moles, remember in the question, it says what? 4 moles of HI was placed in a 5 dm cube flask. So the volume of the flask is 5 dm cube. So you will divide all of these moles by 5 BMQ to get the molar concentration. Right? So to get the concentration of HI, it would be 3.116 divided by 5, and that will be equal to 0.623 moles per BMQ, and then the concentration of H2, 0.442 divided by 5, end up with and I2, of course, would be this same thing as H2. And so these are the concentrations now at equilibrium. So we can go ahead and calculate Kc. It would be if you want to square this, that's fine. And HI. When you work it out, you should get an answer of, and you can break it as well and see, you should end up with 0.02. Can anybody tell me what would be the unit for Kc in this case?
No units, sir.
That is correct. Does anybody doesn't understand why there's no unit here?
So why doesn't have a unit?
Please repeat.
So I'm asking why it doesn't have a unit.
All right. So basically, all right, so this is moles per BMQ, right? And this is moles per BMQ. And so because we square this, it's the concentration squared. All right, let me work it out and show you. Is anybody still writing off the calculation? All right, so let's work out the units. So again, going the long way, the unit for concentration is moles per BMQ times moles per BMQ divided by moles per BMQ squared. That is moles per BMQ times moles per BMQ. And remember, we're going to change this to a multiplication sign and flip everything on this side. So it becomes BMQ per mole and BMQ per mole. And over here will stay as is. And so if you see, this mole will cancel this mole, BMQ cancel BMQ, mole cancel mole, BMQ cancel BMQ. There is no unit remaining, everything is cancelled. So when you solve the equation initially, right? It was moles per dm cube, just using the units, moles per dm cube times moles per dm cube. And because you had squared the concentration of HI, moles per dm cube squared, moles per dm cube squared, it would have equal back to this same thing here.
Sorry, your camera, yeah.
Yeah, several. Right, so I was saying, when you square this, it's the same thing as this. Moles per dm cube times moles per dm cube. It's the same thing as when you square this down here. So both of the units match up. So these two will cancel this right here. So essentially, you would have mole squared, not -2 bm 6. And up here, if you square this, it would have been the same thing. Mole squared bm -6. Right? And so they would have cancelled each other out. But I went the down way just to ensure that you actually see how it occurred. All right. So some persons can work it quickly.
Sir,
Yeah. Go ahead.
For the denominator, it should be mole squared dm per dm cubed to the 6.
Which one?
Denominator, sir.
You mean no? When you're which one? This?
Yeah. Because it's mole per dm cube and
No, I just set it as it would, but when you flip it, then it would have become +6. But I was just putting it as it was in the equation. But remember, like here, when I have it here, so when I have it like this, it's because I was just writing it as it was in the equation. But bear in mind, when you flip it, that is when it will become the +6.
So then you shouldn't have the -2 then?
Yeah, you should have -2, so that means I try to say -2 of the mole, it's mole per dm cube and not mole per dm cube.
Which one? Here, sir?
For denominator, yeah, it should be just a square, not -2, so you just a square. Yeah.
Oh, yeah, all right.
That's what I'm saying. Yeah.
Yeah. Get you. Right. So let me just put up this. So it was dm -6. What was this? Mole per dm cube times mole per dm cube. Mole squared. All right. But if I want to work it, whichever way, if you can do it quickly, you do it quickly. But if not, you take your time and work it out. All right. So whichever way is better for you. All right. So I'm going to put 1 now again on the board and give you some time to work it out. All right. So one more. There's it. All right. Here's it. All right, for the more question, I'm going to have to do it in a video and upload. Because I have to go by school at the moment. So we're just going to have to work this one and close. But I'm going to work some past papers on it and this as well and upload them. Tomorrow we will do some calculations for KP. So in terms of calculation, it is KC and KP. So I've done KC, I'm going to do KP tomorrow and see how much of rates we can do as well. And then in the night, do some transition metals and a little model one. Someone was asking a question.
So we will do group 2 as well tomorrow.
Please repeat.
We will do group 2 as well tomorrow.
If we can, we'll see how the time goes. All right. Yeah.
So you said you were uploading. Where you uploading it to?
Right. It's a YouTube channel. So it's Mr. Here's Chemistry Lectures series. All the classes that I do, I post them here. And when I read these questions, I'm going to post it as well.
Sir, do you also do bio classes?
Not at the moment, but if I have the time, I will send out a link. All right.
So we're using the same link for tomorrow?
Yes, it's the same one for tomorrow as well.
So on what time?
10 o'clock. Okay.
Sir, so no class this evening?
Please repeat.
Sir, so no class this evening?
No, I'm not going to get to keep any this evening. I have some other assignments I have to take care of, unfortunately. So it's tomorrow in the morning to afternoon, and then at about 7 to 10 in the night again. But I would say, by the way, ensure that you have 2 modules comfortable. All right, so module 2 is equilibrium rates and buffers. So with the buffers and pH, I'm going to answer the questions and upload them. And we did equilibrium today, so I want to complete rates tomorrow. So we know that we're sure about module 2, and then in the night, we tackle transition metal and group 2. So that would be 4 out of 6 questions.
When that, sir? When are the transition metals?
Please repeat.
When are we doing the transition metals?
Tomorrow night, about 7 o'clock. Yeah. Transition and group 2, so module 3 in the night. And we try to squeeze the module 1, a little module 1 as well. All right. But I'm going to ensure that you have at least 2 modules covered. So module 2 and 3. Module 1 is atomic structure and moles. Well, we did the redox already from module 1. So I think we should be good enough, right, to do well. And so I'm just going to give you four minutes or so to just answer this, and then I will work it.
Sir,
Yes,
I can ask you a question.
sure.
Sarah, when you're doing the empirical and molecular formula, right? And you get a decimal,
Right.
what do you do about that? You can round it up or just leave it.
No, you can, but it's not with empirical formula. It's a little different from your regular rounding off. So you want the decimal or your answer, you want it to be very close to a whole number. So you see, let's say you get 6.65, you wouldn't round it up, right? And normally, common students to use, if you get, if the decimal is like 0.75 and above, you can round it off, but it's not too early, right? Because I
Okay.
want it close to a whole number. And in terms of rounding off, so let's say you got 6.42, you wouldn't round it off to 6. You want something like 6.25 or below, right? So something 0.2 something or less to round it down. Right?
So, sir, what about if you get something between that? What do you do?
Don't round. Oh, so again, that is when we would multiply. Right? There's a question, there's a unit 2. I was going to work in the class. All right, let us try. All right, let us say we get 6.42, right?
Mm-hmm.
We are going to times it by 2. So 6.42. You are going to get 12.84. If you times it by 2, you get 12.84. And this is close enough to 13.
Okay, sir.
But let me try. I want to find out something.
So, sir, you're about the question, sir. We can't see it. You're about the question, sir.
I'm thinking I did have it already now. Here, give me a second. All right, but I'm going to work again.
So the first question is?
No, this was which one? I am just hold on, just a second. Let me just mute so make it on. All right. I'm going to do the bit for empirical probably sometime late tonight and upload it. So I will explain when to round off, and it's not always just by 2. If you multiply by 2 and you still get, let's say you get 12.65, you would go back to the number and then times it by 3 or 4. But you will keep on doing that until you actually get a whole number or an answer that you can actually round off. Right? But I have the examples. I'm going to work them and show you. Right? But let us just get through this question. So let me just put it back on the board for the person. So allow to come to equilibrium. And for this one, and they say, oh, many moles are present, they are referring to at equilibrium. And then find the value of AC. Does anybody have an answer as yet? I would like to share it.
Is it for CO, is it 0.613?
0.61 for CO, yes.
For H2, is it 2.613?
For H2,
Oh wait, no.
and
So is it 1.839 for H2?
H2, right.
Yes. And for H2 is still 0.387.
That is correct.
Alright, so fine.
From the person that got 0.6, I think, remember for H2, all right, let me put the equation on the board. Remember it was 3 moles of H2. So where was it? CO plus 3 moles of H2. And we have gotten methane and water. So for H2, and so I, C, and CE. Let me see how the question has started again. So when 1 mole of CO and 3 moles of H2 are placed, so we started with 1 mole of CO and 3 moles, and this is just coincidence, all right? It's not always that this number has to be this one. As you had saw in the, or seen in the previous example before. right? And so this would have been 0 because the reaction hadn't started yet. Now at equilibrium, the mixture contains 0.387 moles of water. Now, 1 mole of methane, that means it would increase by X. 1 mole of water, that is X. It's 1 from the balance equation, it's 1 mole of CO, so that would have been minus X. But it's 3 moles of hydrogen.
Hey, sir, can you repeat those X part, please, so the X then jump in?
All right, so when it comes to the change, right, we're just using X to represent the reactants. I mean, the reactants and the products. But we also include the number of moles from the balanced equation.
Yeah.
Because
we know why use the X on it, but one now we come to the conclusion that plus X and minus X.
Oh, the plus. Oh, so the plus just means that. So if you notice up here, it is 0, right? And it is 0.
Yeah, merci.
It's the initial because the reaction hasn't started yet. But as the reaction progresses, the products are going to increase. So the plus sign is just to indicate that the concentration of the products will increase. And the negative sign over here is to indicate that it is decreasing.
Okay, all right. So say you put decrease by 3 times X, because you say 3 moles.
Exactly right.
Okay,
so
all right.
Water is X, that means methane would also be 0.387, and 3X would be 3 times 0.387. So it should decrease. So the H2, it should decrease by this amount. So you're going to work out this and then subtract it from 3. And then 1 minus X, it would be 1 take away 0. Let me carry it over a little. It would be 1 take away 0.387. So this is for CO, this is for H2.
So for H2, I got 1.839.
1.839, yes, that is correct. So let us just put in the answers. 1.839. And for CO, how much I got?
0.613.
Okay. And remember, are these moles or concentration?
Oh.
That is correct. So how would we get the concentration? Because remember,
100 dm.
Divided by
the 10 dm cube, right?
100.
No, it's 10. It's not 100, it's 10.
Oh, right.
A 10. I probably never write it clearly, So just remember,
90 sir.
but in the question, it said that the 1 mole of CO and 3 moles of H2 were placed in a 10 dm cube vessel. So the reaction, right, is taking place in a 10 dm cube container. So the volume is 10. And so just remember, when you get the moles, don't jump ahead to the Kc equation until you work out the concentration. So concentration of CO would be 0.613 divided by 10. Concentration of H2 would be.
Wait, one moment. What we can divide by 10 again?
Please repeat.
What make I divide it by 10 again?
Because in the question, it said the volume of the container is 10 dm cube.
Oh, because mole I work out, so okay, all right.
So we got the mole, but to solve for Kc, it's actually concentration. So we have to divide mole by the volume. And then once we get this answer now, we can go ahead and calculate Kc. No, we got the equation in the question. So this equation, it was provided in the question. All right, so Kc is products, which is methane and water, divided by reactants. So this would be H2 Q divided by CO. Concentration of methane, that would have been 0.0387 times and when you're doing this part of the calculation, remember to put in the numbers. So the 3 here, we have to cube it. All right, so just remember to put in. And the answer we had obtained was 3.89. And I want you to tell me the unit of this one.
I got 3.9. So
Right. I think someone has the DM6, right? So it's DM6 mole -2. Right, since it's the last question, let me just work it out again the long way. And let's just do it quickly. So for this one, it would have been mole over DMQ times mole over DMQ. I'm just going to skip the division part of it. So all of this, we're going to flip it. So it would be DMQ per mole for this one. And then we're going to do it 3 times for this one. So 1, 2, 3. I'm doing it 3 times because it's Q. And then we cancel. And so we're left with VM6 more -2. And so that is how we ended up with it. All right, so unfortunately, I'm going to have to close it here for today. All right. So we're going to pick up again tomorrow.
Sir,